I introduce our three speakers today. Jamie is an architect at Public Architecture, and he's also a certified passive house designer, has been involved in quite a bit of multi-unit projects and residential on Canadian campuses as well. Thomas Bamber and Stuart Hood are both engineers at Introba and are both included on this project. Also both have passive house training. So I know this crowd always has a lot of great questions, so don't forget to put questions in the chat as we get going. Jamie, I'll hand it off to you.
Okay, thank you, Beverly. I'll just share screen. And we'll just expand that. Screen share working okay?
Looks perfect.
Okay, so as Beverly mentioned, we're going to be talking today between myself at Public and Thomas and Stuart at Introba about Vienna House, which is an apartment building that will go into construction this summer here in Vancouver, in British Columbia, which is on the traditional ancestral and unceded territory of the Musqueam, the Squamish, and the Tsleil-Waututh nations. The project's also a partnership between City of Vancouver, BC Housing, which is the provincial funder of non-market housing here in British Columbia, and then More Than a Roof Housing Society. So they are a non-market housing provider they're the current leaseholders of the land, and they'll run it for the full life cycle of the building and manage all the tenant needs. And their social mission has been quite a strong part of the project, and I think it's a really big contributor to the way the building, form of the building, and the priorities of the project. And in terms of kind of demographics, the building's planned for a whole range of different people, families, seniors, people with disabilities, low to moderate incomes, and so on. Just to look at the entrance to the building. In terms of the program, we've got 123 apartments. 45% of them are classified as family units, which is just that their size is 2-bedroom or above. So a little bit of a larger kind of unit type than you might see in market housing. So we've got everything from studio to 4-bedroom apartments. And our 2-bedroom unit is probably the most typical unit in the project. We've also got 230 or so bike parking spaces and just 35 car parking spaces. So City of Vancouver, for a site like this that's located in close proximity to transit, it's got pretty aggressive parking reductions available. So it really helps to maintain, balance the budget on the project and not have to sink too much of construction cost into below ground vehicle parking. Just a kind of aerial look at the building. So one of the issues we've had to deal with is kind of site constraints in terms of spatial constraints, that the site's really hemmed in between an arterial road that you can see kind of sweeping up the page, which is Victoria Drive heading into the city. And then on the north side of the project, there's an elevated railway, which is called the SkyTrain here in Vancouver, which is a line heading into the city center, kind of heading northwest into the city there. Just a broader look at the neighborhood. So a lot of single family homes, and then in a kind of emerging context of multifamily housing, particularly at the intersection that we're at. You can see the big sweeping line above the building, which is the SkyTrain line, and then a large urban park, Trout Lake Park, which is just a few minutes to the north. And just a graphic to describe acoustic analysis. So in addition to traffic noise from Victoria Drive on the west side of the project, the SkyTrain itself produces pretty loud noise levels, sort of up to 80 plus decibels, and there's a train going by every 2 minutes in one direction or another from 5 a.m. to 1:30 a.m. So it's constant noise at a kind of construction site level, and a really obvious site constraint that we had to wrestle with from the beginning. And it really informed our thinking about building form and giving people access to outside space, openable windows, and so on, like how we're going to articulate the building to protect it from this ambient noise. Some site photos. So on the top left, you can see the SkyTrain passing by on the concrete guideway. The edge of the path on the right is where our property line is. So we're kind of building to within about 30 feet of the passing trains. And then on the top left, you can see beyond the SkyTrain, the building has really nice uninterrupted views of the North Shore Mountains here in Vancouver. So I'd say in combination with the acoustic constraints, the desire to get meaningful natural ventilation into the project is a really big component of why the building is shaped how it is. So this diagram just illustrates, on the top, a conventional setup for multifamily housing in North America, where you've got a central corridor, typically no ability to drive cross ventilation. So you're relying on single-sided ventilation, which is not really able to purge warm or stale air. And then the lower diagram is something more akin to what we're proposing in this project. So it's a pair of, or a continuous loop of a single loaded corridor forming a courtyard, which means that every apartment has cross ventilation, daylight from both sides, and we're able to, in terms of kind of night flushing, we can, have windows open on two sides, which will allow us to sort of clean out warm air in the evening. We still have effective fixed and active solar shading, which we'll talk more about. But this diagram kind of, this diagram and the diagram of the noise levels on site kind of really get us to the starting point for building form. So this is just a look at the typical floor plan on the top, and then our ground floor plan on the bottom, which you've got the entry space we looked at earlier that you can move through into the courtyard. And then, as I said, the apartments are all arranged around the perimeter. So you've got exterior circulation, the elevators and both exit stairs are outside the thermal envelope. So you've got exterior circulation throughout. Every apartment has its own passive house standard front door. It also needs to have a 1/2-inch door threshold because of accessibility requirements here in Vancouver. So there's quite a lot of technical challenges. And just to discuss surface area ratio, so this is a slide that we've taken from Passive House Canada's training program about aiming for a surface area ratio of less than 2 for sort of affordable passive house design. So that's the exterior envelope area divided by the treated floor area. And then in our case, even though the building is kind of hollowed out in the center, we're still getting a surface area ratio of around 1.4. I think it's when you get to this level, 6-story development, you can start to do things with building form, which you couldn't do with a smaller building and still get quite an efficient building envelope. If we were building a 3-story building, this would obviously have a much bigger hit in terms of envelope area, heat loss, and so on. So I think it's something I'd like to talk about is whether certain building types, when you're building to the passive house standard, if you can take a different approach as building scale or occupancy changes, that some of the sort of received wisdom about passive house and a focus on compactness above all else, whether we might be able to think differently about that as the climate warms, and if we're building particularly dense housing and we're worried about overheating. And we'll talk a little bit more about that later. So this is just a section diagram through the building with the SkyTrain on the right, showing sort of 73 dBA noise level at the building face on the north, and then 53 in the center just because of the form of the building. And then every time you subtract 10 on the dBA scale, you're halving the noise level. So this would be kind of a quarter of the perceived loudness on the north side of the building just because of sheltering the space in the center. And another important aspect of the project is around social resilience. So we were designing this building during the 2021 heat dome. And I think people in Vancouver and in Seattle got a kind of a real life demonstration of what a 2050 climate event might look like. And in BC, it resulted in hundreds of deaths. And one of the common profiles you would notice among the cases is that social isolation was a major contributor to people having major health effects, major health impacts during a heat wave. So being more connected to your neighbors, knowing your neighbors, and being able to rely on them in a crisis is something that's really important when we think about climate resilience. It's particularly important to our client, and I think some of the evidence of that is visible in the project. And then we were lucky enough in the early phases of design to be able to actually do a comparative model to try to evaluate this social connections between people. So on the right, you've got our proposed courtyard typology. On the left, an alternate scheme, which is more of a central interior double-loaded corridor. And then this is a software called Fluid, which runs on a design team's Revit model and simulates for a 30-day period the social interactions that happen between residents. So you set up certain nodes within the building where people are living, apply certain demographic mix to people, identify where the amenities are and entrance and exits, and then it just runs a study and exports values from there. So we're able to see kind of empirically to reinforce what we knew intuitively, that the courtyard building results in a lot more social interactions and greetings. And then Stuart will talk a little bit more about the sort of mechanical design for the units, but there's been a focus right the way through about having a compact service core, keeping ceiling areas clear, keeping kind of sight lines for daylight and also for natural cross ventilation clear across units. So this is a 2-bedroom unit, an interior view of the 2-bedroom unit. So I'll talk a little bit at the end about building assemblies, but we're using mass timber for the floor system. So here you can see exposed CLT ceiling and kind of glazed openings on both sides of living spaces. So Thomas, maybe I'll ask you now to just discuss some of the design systems.
Thank you, Jamie. Hi, everyone. I'm Thomas. As Jamie mentioned, one of the main drivers behind the courtyard scheme was to generate really good natural ventilation. One of the main reasons is if you can get about 6 air change hours of natural ventilation and you couple this with really robust shading, you can stay comfortable throughout the whole of the summer, particularly in this mild climate that we have in Vancouver. And we have plenty of examples where we have buildings where this is demonstrated. Shading is absolutely key. So if you have too much solar gain, it's unlikely that you'll achieve that comfort through the summer. You can see in this section that we have very effective fixed shading from balconies and walkways. We've also coupled that with Spanish blinds at the windows, and that reduces our solar gain even further while allowing air to flow in through the windows. So being able to keep comfortable throughout, even the high 20s Celsius and the early 30s Celsius is fantastic, and it saves a lot of energy. Obviously, we have to be cognizant of future climate, peak temperature, and wildfire. So we have a mixed mode system in this building. As you can see on the next slide, there's a lot of benefits to mixed mode. What do we mean by mixed mode? Essentially, during the shoulder seasons in summer, you can open the window to get boosted ventilation and that connection to outdoors and to save energy. If there is issues with wildfire, or if it's too noisy or too hot, you can close the windows, and the ERV provides tempered air in summer, which will keep you warm on those peak conditions. Same ERV that does the winter ventilation and treatment as well. And there's benefits to this system. As we mentioned before, a lot of energy savings, which is great for passive house. It also is inherently nimble and flexible in terms of resilience. So if you have a blackout for a prolonged period, you have a system to continue to ventilate and cool the building. If there is a pandemic, we have an ERV and natural ventilation, which are boosting airflow, which is great for health, reduces carbon dioxide, gives you that valuable connection to outdoors. And likewise, if there's poor air quality, you can shut up shop. One of the final interesting aspects is we leveraged the natural ventilation to avoid oversizing the mechanical systems, the ductwork, and to avoid fan coil units. The way we did this is to use an adaptive comfort approach rather than just blanket saying, we will design these mechanical systems to 26 Celsius. So the next slide demonstrates the approach we took, which is the ASHRAE 55 methodology for adaptive comfort. So this is a plot of every hour in one of these units from May through to September. The basic idea is thermal comfort is cumulative. So we can go above the yellow line, which is, we're a bit more tolerant in August because we have different clothing. We can go up to 28 and remain comfortable if we're going up to this extent a limited number of hours per year. And our recommendation is to keep that to 20 hours in line with the vulnerable people recommendation of City of Vancouver. And also to use a more stringent weather file. Next slide. So we use this approach for a 2050 weather file from PKIC. And anecdotally, we actually compared the 2050 weather file to the 2021 heat dome that Vancouver experienced. And it's worth noting that the two were very analogous. In fact, the heat dome was slightly warmer and they had the same number of hours above 28 Celsius. Next slide. So as Canada starts bringing in 2050 weather files as for mandatory modeling, it's worth understanding if your local weather file is already the equivalent of a contemporary severe summer. Next slide. So we'd like to just quickly run you through the methodology that we went through for the thermal comfort with this adaptive comfort method. The different levers, which we are optimizing with this methodology, are the tempered air flow rate, so the size of our ERV, the amount of shading, the amount of natural ventilation we need, and as I mentioned, we want to absolutely achieve comfort for a 2050 climate. So we're going to run through this thermal modeling process, which we carried out using IES. And the next slide shows the baseline design. And for this initial design, we're assuming that occupants will correctly use the Spanish blinds. They will open the window until it's 25 degrees inside the unit, and then they'll close the window again. And we're starting with a 2016 weather file. The 6 units we're modeling on level 6 represent typical units. They're currently all green because all hours are below that adaptive comfort threshold that we saw on a few slides ago. So the baseline is code minimum plus 200% boost, which is a lot of tempered air. The next step was to try reducing the size of our ERV until we were at that critical threshold of 20 hours. So each of the numbers in the spaces is the number of hours which we exceed that ASHRAE adaptive thermal comfort threshold. We've now effectively halved the size of our ERV, which is fantastic. The limitation here is if we actually have a severe year, such as the heat dome, then a lot of these spaces will actually overheat. And the next slide shows us what a heat dome or 2050 year would look like. Actually, this slide is showing what happens if they don't open the windows. So you can see now some of those bedrooms which face southwest are well above our 20-hour limit. And this is still 2016. The next slide shows what happens in 2050 if we stay at this mechanical ventilation ERV flow rate of code minimum plus 33% boost flow rate. So the obvious part of this optimization was to start to ramp up the tempered air that we provide to each unit until we get to the sweet spot where in 2050, we're at that 20 hours limit for every space in the building. So if you come to the next slide there, Jamie, we found our optimized point in terms of how much airflow we need for the ERV and the natural ventilation and the Spanish blinds. And this process, as you mentioned at the outset, has a lot of benefits. If we come to the next slide here, Jamie, we have two systems, a passive ventilation and cooling system and a ERV mechanical system. And that gives you great contingency for various events, be they peak severe heat dome events, a future climate, blackouts, pandemics, and poor air quality. We save a lot of energy, which is very helpful. And we actually have a healthier building in terms of air quality, and also somewhat in line with the social aspirations. We have that connection to outdoors, and we have that connection to our community as well. Robust shading is absolutely key, and having a stringent adaptive comfort methodology can also avoid oversizing your mechanical systems and the need for fan cool units and spaces as well. And I'm going to pass on to my colleague Stuart to talk about some of the other interesting aspects of the systems, mechanical systems design.
Thanks, Thomas. Yeah, so I'm going to run through a couple of the mechanical system features. Just apologies, I'm in a building that I'm not normally in, and there's a bit of sporadic drilling and hammering going on. So if that happens, I might have to pause for a second or two. Yeah, so to deliver cooling to our ventilation air, the most cost-effective solution is to use a centralized system to avoid distribution of piping and fan coils in each of the suites. The heating is provided by electric baseboards, and that's supplemented by heating through the ventilation air also. With the courtyard scheme, locating ERVs on the roof was less favored for a couple of reasons. Avoiding, significant ductwork distribution on the roof to mitigate penetrations, obviously for water, but also for acoustic flanking through that ductwork system. It's avoiding the thermal load on the duct from solar radiation in summer. And so we explored putting the central ERVs down in the basement. It's like one layer of parking there. So what that meant is that we were then distributing through the parking and then shafting up through each of the through the stacks of suites. One of the problems with this, the biggest downside I would say, is that there's a recognized alternate solution to avoiding smoke dampers in multi-family buildings in British Columbia. Which is essentially you're maintaining a 24/7 operation of the system, and then using fire dampers in lieu of smoke dampers. But the intention is that if there's a failure of the units, and therefore you haven't got that airflow mitigating the movement of smoke, is that smoke can then naturally ventilate up and out through the ERV on the roof. And so what you're looking at here is a view of the parking ductwork distribution. So the ERVs are in the bottom left-hand corner. There's two Swigon RX50 units in there. The blue is the supply, yellow is the exhaust ductwork. So it distributes through cold space. So it's still got a significant amount of insulation on it, but not subject to solar radiation, not subject to rainfall on it. So protected from that perspective. We just pop to the next slide. So there's the ductwork layout in the suite. You can see the shaft in the middle there where it's rising up. And you can see that is located centrally between the bedrooms and the living room. And so what we're doing here is that's the only piece of all the ductwork is maintained in that sort of central core area, if you like. So there's the only drop ceiling. And then either side of that, in the living spaces and bedroom spaces, you can see that mass timber that Jamie showed earlier. So there's a 3D view of that ductwork. You can see the shafts there. The green cylinders coming off each shaft are VAV boxes. So there's a pair of VAV boxes per suite. It's controlling how much air is in there. So they're boosting in the normal way. You turn a light on in the bathroom, those things will boost for ventilation rate. If you turn on the range for cooking, it'll also boost for ventilation rate. And then it's also connected to a thermostat in the living room. And if the living room, starts to show that it's heating up, then it'll boost there. And then centrally, we control the temperature of that ventilation. Next slide. On the roof, so maybe just go back one there, Jamie, sorry. But just and what we do at the roof level to allow that smoke to ventilate up and out is that within the insulation layer, there's a thick insulation layer on the roof. We interconnect those shafts and take them to the mechanical room on the roof, where we're able to vent that. So the smoke vent, if smoke does get in there, it's got a path to go up into the duct, into the roof space, and then out onto the roof without transferring between suites, until such time as the fire damper would shut. Okay, thanks. Next slide, Jamie. So as part of the project, we were commissioned by the City of Vancouver to study the available CO2 domestic hot water heat pumps for this project. We looked at 3 different units: the Sandon unit, which was essentially a small residential unit rated at about 4.5 kilowatts of output. The Link by Watts, which is a large unit, sort of up to 124 kilowatts. And then a mid-sized unit, which is the Mitsubishi QAHV, about 40 kilowatts. So they're the 3 that we studied. We looked at the performance of these units at different outdoor air temperatures, sized the systems up for each one, costed them all out. And it's all provided in a report that's published on the BC Housing website. So if you want to go and look into this in detail, you can pop on there and take a look. Next slide, please. So essentially what we're doing, we looked at in sizing these things. The idea is that we size it using a relatively small heat pump volume, but a large storage volume. So in the end, I think we ended up with about 1,800 gallons of 3 600-gallon tanks for these CO2 heat pumps. And then in the end, it goes to a small swing tank, which essentially provides electric heat to do the recirculation volume. So we always keep these tanks as cool as possible. So you see, we analyze them in layers. We sort of break it down and we see, okay, as long as we know we've got enough storage, we always maintain hot water at layer 10 there. Okay, next slide. So essentially, the 3 heat pump systems, obviously all environmentally friendly refrigerant. The vapor compression cycle is well suited to domestic hot water production. And as I said, large storage volume. In the end, we settled for a multiple installation of the Sandon Sanko CO2 heat pump. So we have 18 of those that are configured in 3 modules. They're now sort of put on a package skid. And essentially the reasons for that were cost. There's a few proven installations already in British Columbia. So from that perspective, it's modular, so resilient. The units are relatively inexpensive. So if one fails, you can easily sort of take it out and replace it. And they're quiet because they're designed for single family backyards. And so I get any noise from these units penetrating down into the suites below through wood frame or down into the courtyard below. Yeah, and so if you just go to the next slide, I think you can see what this looks like up on the roof. That's just a view of the roof. So you can see that's a mechanical room with the 3 big 600-gallon hot water tanks, and then those packaged skids of 6 of the Sanko units each. Okay, thank you.
Thanks, Stuart. So I'll just quickly wrap up, talk a little bit about the fabric of the building, assemblies, and so on. If it'll let me advance. Here we go. So We are planning on a kind of a hybrid system. So we've got mass timber floors, but on a light wood frame. So the walls are, 2x4 and 2x6 walls. Pretty conventional assemblies in terms of suite separation. The load bearing system vertically is pretty conventional because we're not going beyond 6 stories or beyond 18 meters of height. So we're not into non-combustible construction or encapsulated mass timber. So as Stuart mentioned, it means that we can expose the CLT in living spaces, which is kind of a nice feature. You see a lot of mass timber buildings that are built and you can't see any of the wood in the end. And then our exterior walls are also panelized and prefabricated. So they are a 2x10 stud filled with dense packed cellulose. We've got OSB on the inside as 15mm OSB taped as the primary air barrier, and then just plywood and the Siga weather barrier on the outside. And then it's got a 2x4 service wall on the inside. So because the way the plan works, most of the exterior walls are non-load bearing. So those 2x10 closed prefab panels are able to be sort of overhang the floors. So it's because they're not supporting the floor edge there, creates a really good thermal bridging detail at the edge. And then one of the other benefits of this type of wall assembly is that for a project like this, where you've got to attach quite a lot of external projections, so walkways and balconies, it gives you solid framing right out at the edge of your wall assembly that you can attach to, and then you can still get continuous insulation within your prefab wall panel in behind structural members that you've added. So for other projects, we've done large layers of exterior insulation, but because of the amount of interruptions that would be required to attach walkways and balconies, in this case, we feel like this is a better, quite a different wall assembly, but better suited to this type of project. In terms of passive house certification, we're on target under the 15 kilowatt hour per square meter heating demand. We're currently at about 14 with some sort of levers that we're still working on. And we've had our PER is at 68, which is over the sort of traditional 60 kilowatt hour limit for primary energy renewable. But the passive house certification criteria now have a relaxation or a project-specific calculator that allows you to get your own PER limit for projects like this that are kind of densely occupied multi-unit housing projects. And then in terms of the name, why the project's called Vienna House. So there is also a Vancouver house in Vienna, which is following a similar pathway. So they're also going into construction in 2023. We've had quite an interesting sort of knowledge exchange with them, meetings every couple of months, exchanging notes on progress and challenges that they're having. Some challenges are similar in terms of cost escalation, but probably more extreme in the middle of Europe than what we've seen in North America. And then other similar technical challenges to do with balcony detailing and site servicing and all the stuff that we wrestle with. So that's been a really nice relationship. And then, as Stuart mentioned, so there is a website for Vienna House, which has all the case studies that have been produced, including their Introba's CO2 heat pump study, a study that Public put together on exterior solar shading options for multi-unit housing, and various other issues. So I encourage you to go there if you want to really dig into some of the technical details, particularly on the hot water system. There's a pretty comprehensive report there, and we'll continue to add to that as we go along. So that's it. So yeah, the project's breaking ground hopefully at the end of June. Yeah, really excited for everyone that's involved. It's been a really great process to get this far, and I've been on a project for 2 years now, so I'm dying to see it start to emerge up out of the ground. Thank you very much.
Hi, I'd like to give a big thank you to the fine organizations that make our work at Passive House Accelerator possible. First, a big shout out to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you too to our founding sponsors, 475 High Performance Building Supply, Baxt Ingui Architects, Glavel, Minutair, Mitsubishi Electric Train HVAC US, Partel, Rockwell North America, Stocorp, and Zola Windows. And thank you to our champion sponsors, Bewiso, Icon Windows and Doors, Intelligent Membranes, Proseco, and Source 2050. And thank you to our patron sponsors, Brennan, Coltraco Ultrasonics, Euroline Windows, Holstrom System, Inotech Windows and Doors, Lamelux, Owens Corning, RDH Building Science, Sanderson Sustainable Design, and US Engineered Wood T-Stud. Thank you, sponsors.
Wow. Okay. Thanks, sponsors. We got a really long question list, so hope you guys are ready. Let's dive into it. We're going to kick things off with, go back up to the list. There's so many thank yous. Hopefully you guys see a love and appreciation for the presentation. Emma in Hamilton, where the House Canada conference is going to be in a few weeks. Emma?
Yeah, look forward to many of you coming to see us. Oh, sorry, in Hamilton. Just a general question is, I can't believe that courtyard buildings like this can achieve passive house. That's so exciting to hear. But I wonder if that is particularly because of the perfect weather of Vancouver, where there's no humidity, or if anyone has seen this or tried it in another colder climate, like where we are in Hamilton, Ontario, or anywhere else. Yeah, just curious about that in general.
I haven't seen a passive house project like this. I think they're relatively rare. Even you know, there aren't a huge amount of examples. If you're in a colder climate, the form factor, the amount of glazed doors that we have. So you know, we've got a lot of door sill details to resolve, because we have, you know, lots of entry doors, which are in a normal building. Those are just on interior doors to corridors. So we've got a lot of those kind of doors. We've got lower door test issues to resolve in terms of the fact that we don't have a common circulation indoor circulation connecting all the buildings. So it does come with some challenges. I think they're all solvable, certainly in the Vancouver climate and in much of Europe. But yeah, it might be a little bit more challenging the colder climate you attempt it in. But you know, there's a lot of other measures you can do, like extra insulation in certain parts of the project that we're not providing, that maybe could be looked at in other climates.
Yeah, well, maybe we'll just try it high level and see if it works, instead of just like, you know, going straight to the box. So thanks for opening that up.
Yeah, this one's going to be a spectacular project. Melvin, over to you. Another person here in Vancouver doing some great things.
Hey, Jamie. Question for you. So I'm just wondering, how does the fire separation work between the suite and the exit corridor, especially when it comes to optical windows and pass doors?
So there is a clause in the code, which is where it's viewed as an exterior passageway. And if it has as long as it's not an enclosed space, if you check the building code, there's a specific definition, which means that wall facing the courtyard throughout the center of the project is not a fire separation, and those doors are not treated as closures requiring a rating. So what we do need to maintain is thinking about 3-meter radius exposure from one fire compartment to another. So where we've got very tight corners that are less than 90 degrees, we have to sprinkler on the inside of some of those entry doors to protect adjacent units and make sure they can get that they can exit without exposure to another unit. But thankfully we didn't have to do anything to we weren't restrained in terms of, you know, providing glazed unrated windows and entry doors on that side.
No, thanks.
All right, we're heading over to Rob.
Hey, everybody. Yeah, really interesting project. And I don't have a lot of expertise on this question, and so it's not really a loaded question in any way. I'm just wondering about the cost issues of doing a single loaded versus double loaded. And does anybody want to have a discussion about the impacts on that?
Yeah, there are targets for floor area efficiency that the provincial housing funder sets. I think what we found is that because the circulation works in a loop, and that it opened up. We were able to get more units per floor with this. We could better use the site geometry. So, you know, I wouldn't say this solution is a solution for all sites in all locations, but for this site, the proportions of it, the noise issues and so on, it was a good solution. And we were able to get an extra unit per floor in this layout versus a long double loaded corridor. And actually the drop in efficiency wasn't as much as we thought. We would think that, okay, this is essentially just multiplying your corridor by 2, but it doesn't quite work out that way. And yeah, we were able to get, I think it's at least 1 or maybe 2 extra units in on every floor. And then beyond that, that's an efficiency and kind of talking about hard numbers. And then there's discussion about livability and having a really constrained urban site with some some serious kind of ambient noise issues that, you know, it starts to build a case from there. But the efficiency discussion isn't quite as obvious as you might think. I think it's worth working through and seeing what you get with each type of configuration.
Excellent stuff, Rob. And again, for those kind of foreshadowing to next week, Rob will be on construction tech. So pin that in your calendar to come back and see Rob's presentation. Hey, just quickly, Jamie, as we switch over to Tom Phillips. This is an interesting site for Vancouver because they've had other showcase projects. It did have a laneway house for over 10 years that kind of came out of the Olympics. Do you know by chance where that Small Works project moved to?
I'm not sure. I think that SFU, Simon Fraser University, was involved in some way with that.
Yeah,
but I actually don't know.
Sean Scott
I've
here.
only
I have the
seen
answer
photos.
for you.
Oh, thanks, Scott.
It's on Bowen Island.
Really?
It's on a
Interesting.
subdivision at Bowen Island. Yeah.
Well, that's great because again, that was really intriguing. Again, talking about, you know, a piece of property that's turned into quite a research project for all these different type of housing. It's pretty exciting. And again, this one's going to be really, really cool to see. Thanks, Scott. We'll get to you in the questions because I know you got a couple. Over to Tom Phillips. Now, I know Tom's happy because there's lots of mass timber in this project, but Tom, if you don't come on, your question was...
I got you. I switched windows inadvertently. I'm so glad to see this project highlighted and excited about it for a while. It looks like one of the best examples I've seen, you know, for overheating prevention and energy efficiency and all that. I'm hope a lot of people follow this example. So thanks so much for sharing that. I did just have a few quick questions, you know, about using the 1990s weather files. I know it's not required, but some groups are doing that. And another question would be, did you do multi-objective optimization for the overheating prevention and things like that? And then carbon savings, you alluded to that in terms of downsizing your mechanical system. So those are just some of the questions that came to mind. But thanks again.
Thanks, Tom. Yeah, I'll try to run through these one at a time. So the 1990s weather files, I understand these were used to inform the 2016 CWEC file, which was the baseline of the analysis. Someone may be better positioned to have expertise on that than I do, but I that's my understanding of those. So it was mainly 2 weather files, the 2016 and the 2050. I
think I meant the 2090. If that was that maybe a mistake.
Oh, sorry. Okay, I beg your pardon. Did we look at the 2080? We looked at it at a desktop level to see how severe it would get. It's safe to say that, you know, the 2080 file is a lot more severe. I think it's good to understand where your additional cooling will come from. Is it more natural ventilation? Is it more shading? We know that we have a bit of contingency in our pocket to say reduce the temperature of the tempered air in future, and you know, the ERV will be replaced after 25 years, so there is scope in the future to upgrade there. Tom, can you just outline what you mean by multi-objective optimization? Sorry, that's not something I've heard of before.
Yeah, there's various algorithms in some of the energy programs that throw everything into a pot and find the best combinations of insulation, air sealing, shading, whatever, depending on your cost criteria and carbon, whatever, you know, the different endpoints are. But and it ends up oftentimes, you know, being maybe even more efficient because you get synergies, you know, at the same cost or maybe not much more cost, and still factor in, and including overheating objectives, which are usually left out. So that's a growing trend.
Thanks for clarifying. So we didn't carry out parametric modeling in the sense of running thousands of iterations, because the tools that we want to use, which capture the thermal mass of the drywall and the wood we're exposed, we're limited to just a few different programs such as IES and Energy Plus, which are less well suited to that. But certainly a lot of iterations were carried out to optimize those levers. And then finally, in terms of the carbon savings of having more modest mechanical systems, Jamie, can you speak to the carbon side of the analysis? Certainly, it's one of the achievements of doing so, and saving energy is one of the outcomes of using natural ventilation. But actual carbon calculations, I'll defer to Jamie.
We do have funding that's just become available to do a whole building life cycle assessment for the project. So that is something that we can look at if we want to get kind of maximum learnings out of it. Is not just to model the MEP systems as they are, but to introduce a comparative analysis. So maybe Stuart and we can see how we can get maximum value out of that question.
Have the final 15 where we're going to try to get through so many questions. I knew this project was going to provide lots of questions. We may not get to it all, but I have a feeling this project might be showcased a few times in the next few years in the accelerator. And of course, if you're ever in Vancouver, definitely hit me up. I will connect with Stuart and Jamie and we go for a tour, because it is a pretty exciting place in Vancouver. So again, if you have to run, again, enjoy the rest of your morning, your afternoon or evening, depending on where on this planet you're joining us from. And again, I know there are a few people here from Canada, because it's maybe because you thought this Vancouver project was be interesting. So just a heads up too, is if you haven't seen Chris from B Collective's Boss project in East Vancouver, he Passos Canada has a Passos Pulse next Thursday, and so a few of the Vancouver faces I'm sure will be connecting on his project. But listen to the podcast before you show up, because you'll get an idea of why he's been involved in creating the Boss. And again, very lucky that provincial policy and grants were available for him to grow that project as well as this one. So again, policy, carrots and sticks, it all comes together. And here we are talking about the Vienna House with Jamie and Stuart and Thomas. Stuart had to leave, but we'll let these two get at it. And Enrique, you're next, and we'll do our best to get through the list of questions. But Enrique, you get to kick off the final 15.
Thank you, Stuart. My question was whether it was centralized or decentralized ventilation, which was answered. But maybe you could elaborate a little bit whether it's one single unit centralized or multi-units, so dividing the apartment, the complex in different sectors of ventilation.
One single unit. So
one single unit. Okay.
Yeah, nice and easy one.
No, great, thank you.
Hey, sometimes the questions you got to start off with the easy ones. Over to Mr. Jason Packer, who is got a less of a beard. The COVID beard
That's
has
right.
been, now you're letting Mark win. I thought you were going to compete with.
It's very dynamic. Yeah, it's Mark takes the beard championship for sure.
All right, Jason, good to see you. Dive into
Thanks. Yeah, great. Awesome project. Of course, we've been watching this right from the beginning. And my question was about the passive airflow. And I'm just wondering, is that all about thermal comfort, or is that accounted for in the ventilation calculations? In other words, are we using the standard ventilation rate procedure for demonstrating compliance with ASHRAE 62.1? And does the natural airflow enter into those calculations?
Good question. Thank you. So just to sort of clarify part of what I presented earlier, we have a background flow rate, which is compliant with ASHRAE and which is compliant with the passive house ventilation requirements for extract for different spaces. When the windows open, the background airflow rate is maintained. So we never actually switch off the mechanical ventilation to each unit. However, the natural ventilation is doing a lot of the work of cooling down the space. So it's significantly reducing the cooling load of the heat pumps.
And so for a lot of our passive house projects, there's this issue that comes up about ASHRAE ventilation rates versus passive house ventilation rates. So your HRVs have the capacity to provide the ASHRAE level of ventilation without relying on the operable windows?
Absolutely. So the building is designed so that the mechanical system meets all of our ventilation requirements discretely from the natural ventilation.
So we always say have the ASHRAE capacity, but run it for passive house.
Exactly.
Okay. Yeah. Thank you.
Thank you.
Scott Kenyon has to leave, and he put in a note. So Jamie and team, again, I will find out who the builder of this project is, but I have a feeling we're gonna have Friday root beers on many Fridays on this particular project as we dive into the kind of weekly evolvements of how this project goes, because there's so much that you guys went through. I mean, I can't believe the kind of thought process of, the acoustical analysis, the natural ventilation, the social resilience, just some new big words to discuss in future projects, and the deep dive that you guys did is just tremendous. Sandra, over to you, our other good friend over in the Ontario world, where many of us will travel to for the Passive House Canada conference. Sandra? Oh, did Sandra leave? Sandra quickly asked, oh, it's funny. I think we actually asked, so what does an extreme weather event in 2035 look like? So yeah, so in your crystal ball, Jamie, besides the heat dome we experienced, what else do you think we could have in dealing with a 2035 weather file?
Yeah, maybe that's a question for Thomas about, I can tell you how July 2021 felt, but the data, and I don't hope not to feel it again for a long time. But yeah, Thomas can maybe provide some input on what the future climate files show for how common or severe that would be.
Absolutely. I think really none of us know what the future holds, but we absolutely need our buildings to be more nimble and more adaptable. The chances of more heat domes happening is very likely. Will it get hotter than that by 2035? I would predict that it will. And we need to consider not just extreme heat, but the opposite, as well as blackouts, as well as continual forest fires. So with Vienna House, we wanted to avoid single points of failure, and that was one of the main benefits of having two systems, if you like. You always have that redundancy. Murphy's Law says that on the hottest days, or when there's a wildfire, that's probably when we're going to get a blackout, if you will. So I think Tom made a good point as well. Do you look at the 2080 weather file to try and understand what the next 20 years will look like? I would say probably yes. And I think it's also worth just interrogating your future weather file with local knowledge, because we've just had 500 weather files issued for different regions. The process that created these weather files is well embedded in science, the morphing process, but anecdotally, the Victoria weather file for 2050 is much more severe, much hotter than the Vancouver weather file for 2050, which is quite odd. So good to interrogate with local understanding and just know what these weather files look like. Are they easy or difficult?
Yeah, Thomas, I mean, I just think back from when earlier kind of passive house socials where we were talking about the Back to the Future data. When Monty was pulling out the Michael J. Fox analogy and the DeLorean about how we talked about the data that just wasn't matching up to our buildings, and the analysis on this, where you look at that future data file and mapped it out to the to the heat dome, and I guess on the extreme too is the Arctic flow and the other temperatures. So really looking at resilience component, and I think a lot of us were always on the sustainability pathway, and how we change the word from sustainability to resilience in these discussions is just really interesting. And like just even taking a snippet and diving into that analysis that probably took you, I don't know, probably maybe a few weeks to really pull the data and examine it, to be able to have that knowledge and review and provide that extra level of comfort to the clients of this particular project is so valuable. And again, things that have evolved in the last 3 or 4 years where we didn't have the knowledge and didn't think about it, and now we're having these deeper conversations to ensure that our buildings and our homes are going to have this extra level of comfort is just, I know, I'm very amazed and blown away by today's presentation, much I'm sure all of us are, and just great insight and info. And it provides more of those conversations that we can have about, hey, did you see the Vienna House? Did you see the data that they did? We should be doing that, like copy and paste this type of procedure, and it's just really invaluable for the degree that you guys had the opportunity to create this stuff. It's just great. Okay, sorry, I carry on. I'm just super excited. Corey, you're next, and we've got a few more minutes. So Corey, try to keep it short. Corey, you still with us? 3, 2, 1. Okay, skipping you. Chen, you have a couple questions or comments. You're next. If you're still here. 3, 2, 1. I know Scott's gone. Annie King, you still with us? 3, 2, 1. No, Bev, you're next. Unmute yourself.
Already got answered.
Good. You're out. Rob Haw.
Yes,
Rob,
hi, I'm still here.
Yeah,
My quick question was, who is the supplier of your prefab walls and flooring systems?
I'll answer it. Go to Passivhaus Together's page on the Prefab Conference and Summit. You'll see a list of all the 12 different companies across North America. One of them will be it. Hint, probably BC Passive House up north. Moving on, Mark White.
Hi, just wondering how you guys are running all of these surface mounted electrical with the exposed CLT.
I'll give you time to answer that one.
How are you guys mounting how are you guys doing all of the conduit and everything for the surface mounted electrical if you've got the exposed CLT ceilings?
So we've tried to we've got our ceilings in our bedrooms are drywalled to give them a little bit, like the 175 mil 5-ply CLT with a normal concrete topping and underlay is an adequate but not exceptional floor acoustically. So we're adding drywall to all the bedrooms, so it's really just that line through the living space. We've got sidewall. We're trying to do as much as we can on the sidewalls in terms of sprinklers and so on, but we will probably have to router from above to the lighting points. So we'll have 2 or 3 lights down the center, and then 1 or 2. We had earlier tried to, because we've got a standard CLT layout, that there'll be 3 panels running, creating 2 horizontal seams across that space. So we tried to coordinate that to profile the butt joint between them, or to profile the joint to basically create a cavity there for wiring, but it may create a little bit too much restriction on lighting location. So we may have to router from above for a small number of elements.
Cool. I'd love to see the construction documents.
We all will. And I think, like everyone else, there's going to be a few open houses where we we convince Chris Higgins and some of the city folk and everyone else involved would be like, we want to learn. We're bringing the cameras. We'll bring Alex and Zach up here and do lots of fun stuff to record all this stuff, because copy and paste. I mean, this is what's great about this project is the showcasing, and of course just means we're all gonna have a trip to go to Austria to see the Vancouver house. So we got to see both houses and compare, right? So get your passports up to date so we can travel abroad and see all this great stuff. Okay, well, that is it. The final 15 is over. Jamie Thomas and I know Stuart Exit, great stuff. And of course, to the Accelerator team, another great show that was put together. And again, exciting stuff, new stuff, lots of great discussions.